All right, welcome back, everybody. This is William M. Briggs. This is another episode of Uncertainty and Probability Theory, the Logic of Science. Today, well, as you can see, it should be 73. Yes, how to discover bad dice. This is going to be, I'm warning you right now up front, this is going to be a long one, a complex one, and I'm going to ask you to have quite a memory as we go through this particular class. But in this class is everything, really. It's kind of like probability from start to finish, and a very common example, which a lot of people get wrong for all kinds of reasons. And the reason we're doing this is because of a longtime reader, Willis Eschenbach, who asked me questions several times. I gave him the answers. I gave him the correct answers, but far too brief. I was just being lazy. And I'm glad that he insisted. He said, this is my third time asking. A couple of weeks ago, I can't remember exactly when. I'm beginning to think you're avoiding me. I have a single die. Okay, I don't have one to show you. I normally do. I don't know what I did with it, but anyway, I have a single die. I want to determine if it is loaded to prefer one face. I could roll it as many times as I want. What mathematical statistic can I use to determine if it is loaded? I say the p-value, but you say that's useless. So what is useless? Of course, the p-value is useless. The p-value is a fallacy when it's put to the use to make tests. We've proved that. I don't know how many different ways we've proved that. You can't use the p-value because you're invoking a fallacy. Why would you want to invoke a fallacy just because of mathematical ease? But I tell you what the p-value does do. It gives you an answer. It gives you a mathematical answer. And because math, it looks like science is being done. And that's the allure of the p-values. It looks like it has measured an objective property of the world, namely probability, and it has told you something about the world. And so the allure of p-values is very strong. And you cannot use p-values. You must not use p-values. We've done, I don't know how many classes on them, at least 4, if not many more than that, and in many other instances where we have proven that the conclusion of a p-value decision is a fallacy each and every time, no exceptions. It is a formal fallacy. It can sometimes give you the right answer, just like any argument can come up with a correct conclusion, but I've done this so many times, but where the premises themselves do not allow you to deduce that conclusion. That's what a formal fallacy is. But you can get right by luck, and so sometimes people do get right by luck with p-values. Okay. Now, all we have to do to solve Willis's problem, it's not an easy problem because of all of the baggage. If we ever have had any training in probability or statistics or anything like this, there's an enormous amount of intellectual baggage, unfortunately, that we carry with it. The answer is going to turn out to be Bayes' theorem. Of course, it's going to turn out to be just probability. He wants to know the probability the die is loaded. We're going to give him the probability the die, we're going to give him, in other words, the probability the die is loaded given whatever evidence that we happen to supply. That's it. That's what he wants. He doesn't want that. The p-value doesn't give you this. The probability tells you about some meaningless statistic, the probability accepting the value of some meaningless statistic, the probability of seeing data you did not see, which is irrelevant. We don't care about data we did not see. We want to say, here's the data we did see. What's the probability the die is loaded? That's what we want. That's what we're going to calculate. And so Willis's version of loaded meant, he said, where one side is preferentially preferred. That could happen. That's one version of loaded. There's lots of other versions of loaded. Of course, if you're going to load one side, we're going to get into physics. We have to. If you're going to load, say you're going to put a weight by the 6, or rather the 1, I should say. You're going to put a weight by the 1 on the other side. I wish I had my dice. I don't know where I put the dumb things. On the opposite side of the 6 is a 1. Maybe you're going to put a lead weight or something inside your die so that it preferentially bottoms out at 1 or tops out at 6. In other words, the 6 is showing. Well, that means, of course, if you're preferentially giving a 6, you might see the other numbers 2, 3, 4, 5, but you'll rarely see a 1. So if you're going to get one number more than the others, it's likely enough, and under certain physics scenarios, you're going to get another number a lot less frequently. But it doesn't have to be that way. Of course, you could have one number more frequently and the others sort of tied in frequency. Okay. Now, I have on the written thing, I'm going to skip it. But I want you to go and read the written lecture. I don't want to put this in the lecture. It's already going to be too long as it is. But I talk about the so-called law of large numbers. And I was reading Wikipedia and looking for examples I could use, other examples and so forth. And they say, and it's completely wrong. I quote it, and maybe I should quote some of this too. They say, the law of large numbers is important because it guarantees stable long-term results for the averages of some random events. For example, while a casino may lose money on a single spin of a roulette wheel, or a dice toss, its earnings will tend toward a predictable percentage over a large number of spins. Any winning streak by a player will eventually be overcome by the parameters of the game. That's all wrong. It's absolutely wrong. The person who wrote that, or persons probably, has in mind that probability is some sort of causal force, or there is some sort of force in there that's going to restore probabilities because of the law of large numbers. It isn't like that at all. And I give another series, a simple geometric series, where we don't accept that kind of bizarre, fallacious reasoning at all. But we do accept that we could have convergence and so forth, and sometimes these convergences, these limit theorems that we have, they may be reasonable approximations to the finite data that we'll always have. All right? So in other words, we could use these limit theorems, and they always go off to infinity. That's what a limit theorem is in various ways. There's the path you take to infinity matters. We've proved that. And Jaynes will prove in chapter 10, or is it 15 of his book, we'll get to that. The path you take to infinity makes a difference. In other words, the way you get to the limit makes a difference, as you can come up to different answers. But however, we can use these limit theorems. There's all kind. The law of large numbers is one, but they state it incorrectly. The law of large numbers doesn't mean anything causative. It's the way they write it is like some demon is memorizing what's going to happen way out in the future and looking back in time maybe and correcting current throws to make sure the sum total of throws, the average throws, the way out at infinity are going to come out right, or I'm not quite sure what they mean. There's nothing, none of those things are right. Or the wheel itself feels this pull towards these particular averages which it's going to reach out at infinity. No. Infinity is a useful thing enough for approximations. And then the end of this thing here, I'm not going to give you that answer. Nobody has the answer to the question Willis asked in infinite terms that I know of. Of course, my knowledge is minimal, so somebody might have solved this problem already. I'm going to do it in a discrete way because, after all, real dice are discrete and finite, as everything is. So we'll get a pretty good answer. I mean, we'll get the answer, but the mathematics is not simple. And limit theorems and so forth, as I've talked about many times, we're out at continuity and we assume continuity and so forth. We often have much simpler versions of the problems that we could work on mathematically. Nothing wrong with that. But the danger and the concern is always the deadly sin of reification, the eighth deadly sin. We tend to start believing that these limits are the real things and the finite stuff we're stuck with is fake and only approximating the limit. No, it's not that way. We're not approximating the limit. The limit is approximating the finite stuff that we have. You have to get the directionality of that right, and that's what the author of, or authors of, the Wikipedia piece on the law of large numbers gets wrong. And most people get it wrong. So that's not going to just be Wikipedia being woke. This is a common error. Okay. And I go on to that more in depth in the article, which will be at wmbriggs.substack.com or wmbriggs.com. You can go and read that and step through it carefully. So let's do some evidence here. So we're going to take some evidence here. Let's suppose we have evidence 1. And this is where I'm going to ask your memory here. This is not going to be a simple thing. We have a six-sided or six-state device which must show one state. Okay? Oops, not parentheses. Okay, now the probability, and we'll let S, just S will be a side or state. A side or state or whatever you want to call it. Because obviously this math or this philosophy works for any particular example we want to use, not just dice. Okay, so we want a probability that the state or side will equal I, given E1, and that's obviously going to be, because of the statistical syllogism we learned well over a year ago, 1 over 6 for I equals 1 to 6. Okay, that's easy. We did that before. Conditional on this evidence, that we know we have some sort of object. It has to take one of 6 states or sides. The probability that it's inside I, for I equals 1 to 6, is 1/6. We deduce this probability. But let's suppose now Willis has said he tossed it, we got some number. M tosses, and that's going to be, M is going to be a vector. It'll be M1, M2, M3, I'll write it all out, M5, M6, because there's going to be 6 possible states. And N, of course, is the sum of the MI. There'll be N times he tossed it, and this would be buckets. He saw so many side 1s, so many side 2s, so many side 3s, and so forth. What's the probability for any M? The probability of S equals I, given E1, for any observation M. Now, if you've been following the class from the beginning, you should be able to answer that, 1/6. And the reason is, it doesn't matter what we observed, because this is our evidence. This says this is what we saw on this side, and there's no way to tie this evidence to this. There's no way to tie evidence of what we have seen about sides into modifying this particular causal, or it's a causal in a sense. Remember, cause is the full possible explanation for a thing. We want the full possible explanation. That's what cause means, the full explanation, the formal explanation, material explanation, the efficient cause explanation, and finally the final cause, the teleology of the thing, the purpose of the thing. We want all that is called the explanation or the cause. So this doesn't seem to be of much help for us, this particular hypothesis. This is a hypothesis, okay, so, but there are other possible hypotheses out there. Let's suppose we could modify this evidence. We could modify this evidence and then relate it to M using some kind of model. And now, we did this before. Then we still have for this will be E2. I had to erase E1 because I'm going to run out of board space. We want to be able to relate observations that we're going to take to the evidence that we're going to have, and we want to be able to modify this. So we know we have a 6-state device that's going to has to show one of the states, and now we have to relate observations somehow to these states. Now we did that. We did that with coin flips, if you like, dichotomous outcomes, which are just 2 outcomes, not 3 outcomes, in a lecture called The Origins of Parameters. And I'll have that link down there, and you can do that. There's just a formal mathematical way you could do that, okay? There's no parameters involved, nothing like this. It's all just counting, and we end up getting a hypergeometric distribution for the 2 states. For when we have more than 2 states, we're going to end up with something like a multinomial distribution, because we're going to have lots of different counts. I'm not going to go through that kind of modeling today. We're just going to take that as a given. If you understand a multinomial, we have slots more than 2. Here we have 6 different slots, and they can only contain a finite number of counts, each one. We're only going to be able to count a finite number of dice throws or state activations, or whatever you want to call it. So we'll have that evidence. Here we don't know anything except for this. We have this particular information here for E2, and we'll suppose n equals 1, which means we don't know before we take n equals 0 rather, before we've taken any of these, before we've taken any observations, we still get 1 over 6 for I equals 1 to 6. I dropped my eraser. After we start taking observations, we modify these things, and we're going to come to, after some period of time, we could just write m, we're going to come to a vector of probabilities. It's going to be, we'll call it p, and that will equal itself p1, p2, and p6. After m or n is greater, this is assuming that n is greater than 1, and n of course is the sum of m. In other words, without getting too complex into the math, before we've taken any observations, it's just like we had the evidence. We know it's going to take one of 6 sides, we don't know which. So every side's equally likely. After we've taken some information, we can modify our evidence to say maybe some sides are more likely than one another, and we'll have this particular n. The probability it takes side, well, I guess side I would be pi, where we have, but for let me put a colon here, will be pi, and we have a vector p1, p2, all the way up to p6, because it's not necessarily true each side is going to be equally likely if we're just going to take these observations. Okay, so this is one possible hypothesis right here that we might use in our theory here. And I warn you, it's just going to get more complicated from this. I hope you're following me, though. The first one never said how to incorporate new evidence, that first theory. This theory tells us how to incorporate new evidence, although I'm not going to show you the math. I'm going to refer you back to that origins of parameters thing. And in the end, it's going to be something like a multinomial distribution. And we could write that up on the board. Okay, so that's, which is not the most important thing. That multinomial distribution or the hypergeometric distribution are not the most important thing. The point is, we're after this. Here we're talking about the probability of taking sides, given a particular hypothesis about a particular device or die or something like this, given observations. Okay, after we give an observation, what's the thing? But this does not, of course, exhaust all possibilities. All right, I want to make sure I have the notation. Okay, so now, this is where it starts to get tricky. You got to rememberize all this stuff right there. Let's do this. We're going to have E3, which is the die is loaded. Okay? This is a causal I don't know why I keep putting parentheses around these things. Math coding habit, I guess. The die is loaded. That's a hypothesis. That means when we're talking about measurements, we can see side equals I given E3 equals some Qi, where Q is itself a vector Q1, Q2, Q6. And of course, all Qi are not 1 over 6. That's what loaded means, after all. In other words, the probability it takes any particular side is going to be given by some Q. We got to understand what the proposition here we're trying to do. This proposition is a causal proposition. It's telling something about the physical state of this particular die. It says it is loaded. That tells us something about the toss. We'll talk more about this in a second. Given that hypothesis, the probability is going to be some Q. Qi, any particular state, where Q is another vector for 1 through 6. And we know that the Qi are not all 1/6. If they were all 1/6, the die would not be loaded. It would be something else we'll talk about in a second, okay? Now, let's suppose, I could do this. I did in the writing, I'm much more careful about all this. But let me take some data now. I hope you follow this. I'm seeing some nods here through my clairvoyance or precognition of people's in the future looking at this after Thanksgiving. It's a week after, and your bellies are now emptying out somewhat, and you'll be able to follow me here. This says we know the die is loaded. Therefore, the probabilities can't all be equal to 1/6 each side. We're deducing these probabilities, okay? We're deducing these probabilities. Now let's add some observations. Whatever we see, how we roll the dice so many times, whatever we see. What's the probability now? It doesn't change. No change. C-H-A-N-G-E. Good grief. Can't spell. This is crucial. We add evidence to this, it doesn't change because we know the die is loaded. We're telling something about the physical properties of this die. And we'll talk more about that in just a second, but just press the I believe button for that for a second. We got the die is loaded. We know it's loaded. We deduce these probabilities based on the physical knowledge of this die. The causal knowledge we have of this die is Q. And then we're going to start tossing it. We know it doesn't matter what the tosses are going to be because we know the die is loaded. We're conditioning on knowing the die is loaded. All right? This is not the probability that this hypothesis is correct. Probability of seeing the data is not the probability of the hypothesis itself. Okay? That's not the same thing. That's the big mistake the p-value makes. We're assuming here it's loaded. And from that loading, we can deduce this Q. And therefore, whatever data we take doesn't change these probabilities. That's crucial to understand. And it's also crucial to understand we're not looking at the data, and we're not looking at, and with some background information here, we're not calculating this, okay, which we're going to talk about here. Do I talk about it now, or do I talk about it in a second? Oh, I do talk about it now. I've maintained some kind of consistency here. We have to have some background knowledge. We always do. We talked about this from day one. At least the background knowledge is it gives us knowledge of what these symbols mean, what the mathematical symbols mean and how they relate to reality, and it gives us the tacit, implicit information that we're assuming just to be able to do this problem. It's all in that B, background information. Sometimes I use E. For here, for other reasons, because I'm using this. Why did I use E? I have no explanation for you. I used E, and then I kept going with it, and then after that I realized it was too late to change to something sober and sane like H. So yeah, this is the problem about notation. I warned us from the beginning too. It can help or hinder. Okay, so B tells us this. Now, if B says, B says, well, I know it's E3. And therefore, the probability of E3 given B, no matter what we've seen, is 1. If you say, I know the only hypothesis that it can be is E3, and then given the only hypothesis I know is E3, the probability E3 is true is 1. It is a local truth. We have deduced this truth, okay? So the truth that the die is loaded is 1, assuming we know the die is loaded. That should be absolutely clear to you. And because the die is loaded, and whatever observations we've seen are irrelevant because we know the physical causes about this. So now let's talk more about that kind of a thing. Okay. Now here we're going to give another one. And I don't think I write it out. Maybe I do. Do I write that one out? Yes, I do. I have to erase this. Let's erase this. I really hope you're following me on all this. It's going to get more complicated here, and it hasn't been easy so far, I think, and we're halfway in done. Let's introduce a new hypothesis, fair. You'll see this one written all the time. Fair. What's the probability? And what people kind of have a vague idea that decide, given E4, and I'll just put this in here, and I'll start writing the B in here, is 1/6 for all I. The die is fair. You'll see this all the time. Pick up any textbook, probability textbook, or statistics textbook, introductory statistics textbook, and they'll talk about fair die and fair coins. Now, what could that possibly mean? What could that possibly mean? Well, it must mean that we can deduce the sides are all equal to 1/6, for a die anyway, given our background knowledge. But it means something a lot more than that, because look, it must imply that there is symmetry. Because we know that tossing a die is a physical process. And here I refer back to the video we did a long time ago. The probability of a coin flip is not 1/2 of a head on a coin flip. The probability is not 1/2. I and my father, we built a machine, a coin flipping machine that comes up heads every time, because we control all the causes and all the conditions of the coin flip. All right? Knowing those causes, we can predict with certainty. There's nothing random about a coin flip, unknown, when you know the causes. Okay, well, I'll write this up in notation in a second. And the same thing is here when you're saying the die is fair. That must be saying you have a die which is absolutely perfectly symmetric on every possible dimension. It has 6 faces, it has all of the lines, it has edges that must be absolutely perfectly thing. The pips are drilled out, usually drilled out and then painted, which right there provides an asymmetry, right? On the opposite side of a 6 is a 1 pip or 1 dot. And then there's 6 over here. This is taking out a little bit of a mass from this side and giving a little bit more mass to the 1 side than the 6 side. It has to, because we've taken less mass off the 1 side than we have the 6 side. You think, oh, Briggs, that doesn't matter. Yes, it does. It absolutely does. We're talking about a physical process here. We're talking about a physical process. We're just basically so used to saying it's such a little bit, it doesn't make much difference or a noticeable difference. Aha, that's not the same thing as saying no difference. This is the absolute crucial part. Okay, so we got this die. And the symmetric weight distribution inside is precisely the same. The surfaces are exactly the same amount of friction and resilience and reboundedness and every other property that you can think of that might be causally important in how a die comes up. But that's not, dies don't toss themselves, and they don't toss themselves nowhere. So in order to talk about symmetry, you're not only talking about in the die itself, but you're also talking about in the manner of the throw. In other words, you're talking about perfect symmetry. What is this? It's coming off somebody's sweaty palm. What does that mean? All palms are going to do that, are going to have equal friction of the skin surface and equal moisture content and all this kind of stuff. And the gripping power of the fingers is going to be duplicated, or at least it's going to be symmetric in all possible ways you can grip that die. And of course, all possible ways you can grip that die. This is a 3-dimensional object. We can rotate it in space in a lot of ways. The manner of tossing. And then finally, I call it the milieu of tossing. That die has to be tossed somewhere. If it's in a casino, it's on a board covered in felt, and you have to hit a back wall if you're playing craps. And they have these, usually they have something that sticks out, these things like pyramidal kind of things that jut out a little bit or something like that. And the milieu is important. What do you mean by symmetry in this milieu? There's all kinds of physical possibilities that are going to go on with this milieu. The felt itself can be more or less slick everywhere, or more or less friction depending on where. The back things can be more or less bouncy depending on how much wear they have, and the absolute atmospheric pressure can be important in this milieu. Of course, if you're up higher, the dice are going to fly freer than if you're down lower. All this stuff. So when you're claiming a die is fair, you're claiming the die is symmetric, the manner is symmetric, the milieu is symmetric. This is an incredible statement. An incredible statement. This is if they used to tease, the schoolmen, the scholastics, for angels on the head of a pin. This is angels on the head of a pin playing craps. This kind of stuff. But nobody ever thought it through. A real die, of course, I practice amateur magic. I could tell you it's a real die. Any number of things can happen where the die is loaded, any number of things. To claim that you have perfect knowledge about this right here is extraordinarily strong. It's extraordinarily strong. This is maybe the strongest possible piece of thing that you can claim about some process that's so difficult. I'm going to call this symmetry knowledge K. And I didn't want to use P for physics or S because I already used S for psi. Just see about notation? So I'm going to call this knowledge here that perfect symmetry in the die, in the manner of throwing, in the milieu, is impossible. Not possible. In other words, the probability that E4 is true given K and anything else is 0. You're not going to get it. It's just absolutely not going to happen. Which means if our background information is we have something like, what did we say here? The die is loaded, E3 or E4 is true, and we want the probability that E3 is true. I hope you're following me here. Given B and K, the probability the die is loaded is 1. So there's Willis's answer. Every die is loaded. Every real die is loaded. That's the answer. That's absolutely the answer. Every real die is loaded. And if I want to know, okay, so let me just make sure we have all that. Gee, this is a point really I wish I could just look at people's faces and see if they're getting this. Assuming K, which on background information we have about physics, K itself is true. It's just true. You're not going to get a symmetric, perfectly symmetric manner, milieu die. It's not going, or I should call this, hey, I just saw this. Now I got the 3 M's. Material, manner, milieu. The 3 M's, you're not going to get it. It's impossible. Not going to happen. All right? And if you're objecting in your mind saying, well, it's close enough, that's not the point. That's not the point. The fair says that this K is true. The K cannot be true. Therefore, the probability that if we're only considering the die is loaded or E4 in the face of K, why the probability the die is loaded is certain, and the probability of E4 is true is false. It cannot be false. Okay. Well, all right, that's Willis's answer. The answer is, how do you tell if the die is loaded? The answer is 1. But that's not very helpful, right? I mean, it's true. This dumb thing. Come on, wake up. I want to make sure I follow the notation I've used in the thing. You could also write up, and I'm not going to write it up here. You could write up if you knew the causes. If you could control the causes like I can as a magician. Maybe I just will write 1. If you want to control the causes, the probability of a side equaling I, when you know the causes, and it doesn't matter what you've seen previously, is going to be either 1, it's going to be 0 or 1, depending on what the causes say for any particular throw. Right? Just like the coin flip machine. I know what it's going to be because I rigged the machine. And if you know the causes of the die, all of the causes, like you have a trick die, which can be a loaded die, but you have a magician's die, let's call it, which I have some of, and I don't know where I put the dumb things. Okay. So that, if you know those causes, then the probability of the side is either 0 or 1, depending on the side considered. Okay. I go through all that kind of stuff. But that's obviously not what we're going to see here because we have tacit information in B here. My tacit information kind of tells me, based on Willis's request, that he's not thinking of something like this. If you're going to roll a die and every time it's coming up 6, 10, 20, 30 times in a row, you don't need a statistical test. You don't need formal probability. You don't need any of that. I mean, unless you're trying to think about peer review or something goofy like that, some idiotic academic request. We don't need any of that. That's obvious what's going on. My idea is Willis is looking at dice that may be good and may not be good, which means something else entirely. So we need to introduce a new hypothesis. We need to introduce yet a new hypothesis because we have proven that this one's true given our knowledge of physics. And we're done. Okay, we don't necessarily know what these Q are unless we know all of the physical attributes of it, but we can go back to E2, which allows us to take information we have and then find those probabilities, okay? But we got to remember the gambler's ruin problem. Remember the gambler's ruin problem, or the gambler's fallacy, I should say, problem. A gambler is looking and he's at the roulette wheel, or he's tossed the dice so many times and he's seen 6 come up. And I guess at craps you have to have 2 dice, but you can roll a 6. A score of 6, and he's seen 6 come up 4 or 5 times in a row. Oh, now he's saying other numbers are due. And he will miscalculate based on that if the dice are in fact closer to fair than not, and he will go broke and the casino will make even more money. So you have to be awfully careful here, and that's why we're taking so long. So let's be awfully careful here. Let's introduce all right. Let's unfortunately we have to make space here. That's the advantage of the writing. I'm going to change the writing. I think I have time to the manner, the material, manner, and milieu. That way I get 3 M's, and that's always more memorable. Another M. Okay, let's have another hypothesis. Casinos. We're going to think first in terms of casinos. Very obviously, if which one was it? E4 was correct, and we do have symmetry, perfect symmetry in the material and the manner and the milieu. If we have that, then the probabilities we deduce are 1/6. That's what the casino wants. They don't want to have it shaded any other particular way, because then they would make less money. They want to maximize the money that you're gambling, that you are gambling, that goes to them, which is one reason they call it gaming and not gambling, because it sounds like you're having fun when you're only gaming and not just giving them money when you're gambling. Okay, we'll call it assiduity. So in other words, the casinos are careful in their choice of manufacturers for dice. They come out of the box looking symmetric as can be. You know, the manufacturing processes are careful. They've used these dice in the past and had no difficulties with them and things like this, knowing there's going to be some departure from symmetry all along the path. Now, Willis is only interested in the material part of the departures from symmetry. So we're not going to consider here departures from the milieu, departures from symmetry from the milieu, or departures in the manner of throwing, although those can certainly exist. So we'll consider only departures from symmetry in the die itself. There will be some symmetries, asymmetries I should say. There will be some lack of symmetry in any real die, any real dice. And that's what J tells us. J sort of incorporates K. J and K, if you like using Boolean notation, just equals J. We know that we're not going to get perfect symmetry out of this, but we're going to be very careful to try to get as symmetric as we can. Okay, so now finally, with all this in mind, trying to think physically, causally the entire time, because that's the whole point of science, trying to think physically and causally, we come up with, let me see if I have the notation here. We can come up with other hypotheses, okay? And we're very careful to talk about these hypotheses are of the dice themselves. They're not about the probabilities. We deduce probabilities from the hypotheses. But sometimes we write up shorthand that makes it look like we're talking about the probabilities. And if we're not careful, which most are not, we'll end up talking as if the probabilities themselves are the hypotheses. But nothing can have a probability. Probabilities are deduced from the hypotheses. So the hypothesis was E4, symmetry, from which we deduced the probabilities. All right? The probabilities of 1/6 uniformity was not the hypothesis. The hypothesis was symmetry, from which we deduced uniformity, okay? We have to keep that ever in mind. So, Now, well, I'm going to keep, you're going to have to remember J and E3 and E4 and all that kind of stuff. You're just going to have to, stick with me here. This is why I said I was going to tax your memory here. The problem is, here's the problem. We might accept. We don't know whether or not J will be true for, it's true everywhere. But this is the problem, depending on B. That background knowledge is still there. The background knowledge and J tell us no dice is going to be perfectly symmetric, and they aren't. So therefore, we don't need to have, we have most of the mechanisms. Really, it turns out then to be that E2 and J and E or E3 and J, this is where we had the probabilities came out as any kind of probabilities we were going to deduce, P's, and this came out as Q's based on the knowledge of the thing. Well, we can't, unless if we don't know the knowledge of how the dice works out, then we're sort of left back with E2, where we don't know what the probabilities are going to be. We don't know what the falls are going to be, okay? We do know that there's asymmetry. And now we're going to try to make predictions based on that asymmetry. So let's have some competing hypotheses here. I hope that makes sense. If we know the properties of the die, we can deduce these Q, and it doesn't matter what we see, right? If we don't know the properties of the die, but we know J is true, we have to somehow calculate these P, the probability any particular side is going to come up. And we know something like that is going to hold. All we know is the probabilities will not be perfectly symmetric, okay? We haven't, in here, the only thing we can deduce out of this is that symmetry is not available to us so that the probabilities won't be 1, 6, 1, 6, 1, 6, 1, 6. But that's still we can call that, let's call that E good, where, and now we'll have E bad. We'll have E good and E bad, EG and EB. We have two hypotheses here. We're good enough, this will be good enough, close enough, good enough, close enough, deduce probabilities, and not close enough. And in the face of, and K, or J, which also incorporates K, is part of these hypotheses. In other words, we have a dice. We have a die. Suppose EG is true. Suppose EG is true. Then we're going to have a probability of a side. Side I. Side 1, for instance. And we know that EG is true, and we have our background information right here. This, well, we're going to have some M. We're going to take some data in here, too. And then we're going to have the probability of S2 given EG, MB, and then so on down to probability of S6, EG, MB, okay? This will give us some P1, this will give us some P2, and this will give us some P6, all right? Which we're hoping are going to be, for a good die, are going to be 1, 6, plus or minus, say, epsilon. Oh, that's a very lousy epsilon and a very lousy plus or minus. Okay. Plus or minus, oh boy. Try to do an epsilon in the minus. Plus or minus some epsilon, we'll call it that, okay? And this will be 1, 6, plus or minus some epsilon, and so forth, plus or minus some epsilon. Now, how big is epsilon? Well, that depends on the uses to which these problems are going to be put. If you're pulling out a board game you just bought from the Goodwill and it's a rainy afternoon and you're sitting around the campsite and nobody's got anything else, you're sitting in the cabin rather, nobody's got anything else to do, you don't care about any of this. So the epsilon will be whatever, you don't care, it's close enough, all right? The probability these dice are good is close enough, is going to be good enough for you, unless one's missing somebody shaved off the faces so you can't tell, and then the probability the dice are bad. So it depends on the uses to which you're going to put. There is no universally good, there's no universally bad. Okay, that's key. It's not going to be like a p-value or some nonsense. There's nothing going to come out to be we have to decide what's close enough, what's far enough away, and so forth. All right, probability bad means that it's going to be greater than, plus or minus greater than epsilon. Oops, I shouldn't do that. The probability is for SI under EB, using our background information and whatever we see, is going to be some probability we deduce for every side would be 1/6, you know, plus or minus something greater than epsilon, something like this. You could see, I hope, that the possibilities here are very large. I'm already at 45 minutes. I knew this was going to go at least an hour. Here, we want the dice at close to symmetry as we can get it, knowing we're not going to reach perfection. Meaning the deduced probabilities, these are deduced probabilities based on this, will be close to 1/6, not too far off. Not too far off depends entirely on the applications to which you're going to put it. That means the probability of a side, assuming the dice is bad, is going to be worse than 1/6 plus or minus this small thing. It'll be worse. That leaves lots and lots of possibilities, okay? So for instance, one possibility, of course, is Willis's example. I think he said he wanted to weight to 6. So the thing is here, it's going to be, it'll be 1/6, 1/6, say 1/6, 1/6, and this will be a little larger than 1/6, and this will be a little less than 1/6. The 6 spot gets a little more than 1/6, and the 1 spot, because we're putting a weight in his particular example, gets this. But there's all kinds of other possibilities. The 2 could be less than 1/6. All of these could be equal, and this one could be larger. Or there could be any number of combinations that we can go off and depart from, right? There could be, we could add, as long as the sum of pi equals 1, or even here the sum of the pi has to be 1. The sum of the probabilities has to equal, something has to happen. As long as we have that constraint, we have lots of possibilities for bad dice, right? Okay, so now let me erase all of this again, and we'll use that. And here finally, we're finally getting to the real answer. We're finally getting to the right answer. I hope it's making sense. I have the article I wrote on this is 4,000 words long, so you know I have a ball reading this. And I wanted to make out I did some numerical examples here, and I'm going to have code here in a minute for you to see about all this. All right. Now, I'm going to use the terrible shorthand that you should never use. Well, that is to say, I'm going to suppose because I want to make a numerical approximation of this. I don't want to make the problem so difficult that it can't be solved. You can already see that there's so many possibilities. And in one routine that I wrote, I checked 72 million possibilities. Because I did everything finite and discrete. Here is where there's plenty of work to be done. Here's where I said I don't know if the solution's known or not. You can specify exactly what you mean by good and bad. And then you could use an approximation to these things, a continuous approximation such that the probabilities can be computed more or less exactly as an approximation to the discrete and finite thing. I did the discrete and finite thing. So, but it's very difficult to keep track of stuff. So I'll show you what I mean. Okay, I'm going to suppose this is symmetry from which we deduce the probability vector 1/6, 1/6, 1/6, 1/6, 1/6, 1, 2, 3, 4, 5, 6. Okay. Now I know that isn't exactly right, but that's what I'm going to consider good. The 1/6. and I'm going to ignore small departures from deduced probabilities from this, because I just want to get a reasonable answer, and I don't want to try to calculate every possible other value of good dice. In other words, I could have plus or minus epsilon to all these things, and I could add those probabilities in, but it's not going to make that much of a difference, as you'll see in a second. And E bad, just for the first take, I deduced the probabilities. What did I use here? I used the probability vector 1, 6 minus A, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6 plus A. So that kind of gives the 6 spot loaded one. Okay, bad. This is bad. This is just one particular example. All right, here is I can't stress this enough again. Why did I choose these two things? Because I'm the one who chooses the hypothesis. The problem doesn't give you the hypothesis. That's another problem with p-values. I'm the one who chooses the hypotheses. I'm the one who brings cause to data. I don't extract cause from data. I put it in and then I ask probabilities. That has to be key the entire time. Why did I pick these two things? Why did you name your dog Spot? All right? It's your choice. You're the one who brings these things to probability. So I decided these were the two hypotheses. Later, I'm going to expand this one. I'm going to expand this bad one. I decided these were the two hypotheses I was going to check. Now I need to have in my B needs to specify prior probabilities of whether or not these are true. Now if my B incorporates J, which is to say the assiduity, I'm being very careful, I'm the casino buyer, purchaser, whatever they call them. And I'm the one who sources the dice for the casino. I'm going to be very careful. But if you're not, then you have to use I'll talk about that in a second. But I was going to say, because there are videos out there. I saw this video a long time ago, and I don't know if it still exists, and I haven't been able to find it. A guy got these Dungeons and Dragons dice, these 20-sided dice, and he got a bunch of them. I forgot how many, a dozen or something like this. And he lined them all up. What's it? Is it 20 and 1? I've forgotten. And 20 laid out all the dice, 1 to 20, 1 to 21. So they were all in a row, all tight together. Measured it. Came out to be so many inches. And then he did the opposite faces, not the opposite faces, but the orthogonal faces, and lined all those up. And that turned out to be a completely different number of inches. So the symmetry was missing. And he did experiments and everything showing, of course, the probabilities of getting the top roll of a 20 or something like this was departed from symmetry. All right, so this guy did the physical measurements on the dice exactly the right way, and did all the, exactly what you should be doing with these kind of things. But if you're a casino, of course, you can't really do that so much. You have to trust from batch to batch and so forth. So whether or not we depend on J depends on so I'll subset this J right here. I want to have the prior probabilities for EG based on my background knowledge and EB. I decided to go with this. In other words, if I'm the casino buyer buying from the guy who I'm always been buying from, the manufacturing of these dice, and they've provided good results for me in the past, I'm going to assume that this is the case for the next batch I'm going to get in and test, or single die I'm going to check. This is me. You don't have to pick these particular things. I'm going to give you the formula here in a second. You pick whatever ones that you think are right. If you don't have J and you just have B, and you're buying, you're going to some cheesy, shop down by the school or something like this, and maybe you want to do 50-50 for the two hypotheses. You're just buying some crappy. I guess they're all plastic, aren't they? I don't even know. Some of them are very hard plastic, or maybe they use different things in them now. I don't know. I don't know about that. But some of them are really cheesy plastic, and some of them are high quality plastic. So maybe for that particular, without the J, you want to have 50-50. That's up to you. You bring that knowledge to the problem. But I'm going to show you it doesn't really make too much of a difference. That's one of the mathematical findings of Bayesian theory is the more information you collect. In other words, the more, the higher n gets, the less weight this has anyway, and so it's not crucial. But it's reasonable. You're opening up a box of dice from the manufacturer that you've been using forever, and you're going to pull one out, and I'm going to make a bet with you about the first one being fair or not, being loaded or not, being so far out of tolerance, I guess I should say, instead of loaded. But it is loaded. We already proved it. It's going to be loaded. But we're going to say it's reasonably good or not. And you would use this as your particular information. It's a real-life decision problem that you might come across. Okay? But now we're going to take some data. And for whatever reason, and I just use this for fun, and I'm going to provide code for you so you can plug in your own numbers. I use the vector 1, 2, 3, 4, 5, 6 times c. And for my first one, I just did c equals 1. And that gives an n of 21. In other words, I thought I rolled the dice, or the die, 21 times, and I got only 1, 1, 2, 2, 3, 3s, 4, 4, 5. Why not, right? I have to have some example right here. And I got to keep this awake so I can give you the exact probabilities I found here. Makes sense, right? Now what do I want to know? I want to know the probability that E bad is true, given my B and my M. That's it. That's what not Lewis. Why do I say Lewis? That's what Willis wanted to know, right there. Here's our evidence, and here is what loaded means. Finally, we learned that loaded means EB. That's what I want to know. That's it. We finally got to the answer for this particular problem when my background evidence said that these are my two hypotheses and these are my priors. That's just Bayes' theorem, right? It's the probability of seeing M given E, B, and B times the probability of EB given B divided by this same thing. This Japanese pencil is neat, but you have to keep pressing the button, which is annoying. PEB given B plus, okay, that's just Bayes' theorem here. We've done this a million times. I'm not going to, or the probability of the data. Come on, baby. Maybe it's empty. I got others. Probability of the data given, we assume, the data is good, or the data is good. The die is roughly symmetric, okay, within the bounds of J, which we're assuming is part of our background information. B times the probability. Come on, baby. You got to have something left in you. The lecture's almost over. Probability, oh, no. The probability of B. Okay, that's it. There you go. There is the answer. Simple as that. For this particular problem. For this particular problem, the probability the die is loaded when I'm considering close enough to symmetry, my understanding of J, and bad meaning this departure where, oh, I didn't specify the A. I think I used A equal, that's a good question. What did I use? I used something. I got to pick an A. For this particular problem, for the first understanding, I picked an A, and I used 0.001. For a casino, I assumed we did not want departures greater than 1 in 1,000 from deduced probabilities of 1616166. We didn't want to have departures greater than 1 in 1,000 because dice get used frequently. I guess they retire them before they maybe even hit 1,000 rolls. I'm not even sure. So that seems like a reasonable number. I don't know how many throws that they make with individual dice before they're retired or they're sent out of service because they wear, because they're keeping this J and K in mind the entire time. So they have that entire mind. So I thought 1 in 1,000 seemed reasonable. If you don't think it's reasonable, you stick in whatever numbers you want. So this probability turns out to be, for that, I have to look it up what I did. I didn't memorize any of this stuff. It turned out to be Ta-da. Where'd it go? I know I did this. Anyway, it turns out to be, I happen to remember what it was, 0.00010, I think it was 4. For somehow, it got erased from my, I'll have to go and edit this thing. I'm looking right at it here. No, it's 103. I did not erase it. I have a typo. That's what it is. Mr. Typo. My enemies put typos in, even in the stuff I'm working in. They put typos in everywhere I do it. It's just, it's, is that 21? 6 times 7, 43. 42 divided by 2, 21. Yes, 21. Yes, okay. So I thought I did the math wrong, but that's it. So that's what we get. We get 0.0103. So if we saw this particular thing, we saw 1, 2, 3, 4, 5, 6 for our collection of data. We calculate the probability of seeing that data under the hypothesis the thing is bad, meaning it's off by this much, and that's some probability, using the multinomial, which I'm not going to write out for us here, but we just calculate the probability of the data that we saw, assuming this hypothesis is true. We multiply it by its prior, and then divide by that same thing, and then the probability of seeing the data, assuming the it's close enough to symmetry for our work, and the probability that it is symmetric. And in the end result, we get that. Simple as that. Is that big enough a departure from that you would make a decision based on that to throw out this batch or something? I don't know. There's no answer. All right. This is the other big key here. There's no answer. There's no right or wrong answer. It depends on the uses to which this kind of information is going to be put. I don't know what you're going to do with this. I don't know what the casino is going to do with it. If that's what they saw, maybe they're going to do more. So that's what I did. I said, well, maybe we'll do more. So I said, multiply the lot by 10. So I let C equal 10, which makes n equals 220. And then the probability turns out to be 0.0013. Do I have too many zeros here? Yes, I do. 0.00, I have too many zeros there. I have it right in the write-up. I don't know why I did that. 0.0013. In other words, if we saw 10, 20, 30, 40, 50, 60, it's just easier to multiply by 10. That tells me now I have a 0.0013 chance that the data is bad or the dice is loaded. Is that big enough for me to do something? Probably it is if I'm the casino. That may be too big for me to, depends on the loss, it depends on the gain, depends on the decisions. There's no right or wrong answer. Statistics does not provide a right or wrong answer. It just does not exist. Okay, so you can go through it all this, you can play all this, but this is kind of like an introduction. It's not very satisfying. It's because you may not know the data is loaded for 6. What about the other hypotheses where the 2 has got the minus A, or the 3 has got the plus A, or any combination? Or what about other possibilities of A? I only did one possibility of A. Symmetry seems pretty obvious. We'll keep things that are close to 1/6, but I want to check other possibilities. Okay, so I'll leave this up here. We actually have, and I'll leave this because I use this. This is just my example. We basically have this problem. We have P equals every PI plus or minus some A, plus or minus some A, subject to the constraint where the sum of the PIs equals 1. And where A itself is positive. Now I did this. This results in quite a lot of different hypotheses. All it does is it gives us, for every possible different A, we have a different we have a different bad hypothesis. And now you see why I have this advantage of being able to erase this. And all I'm going to do here is this. I'm going to sum over the i's. I have E bad I, E bad I. Okay? This is supposed to be a sum. And you'll see this on the blog. It'll be much easier. So in other words, I'm going to consider all of these possible hypotheses where I'm going to let A be greater than 0, and I'm going to have 1/6. This is, sorry, 1/6. Every one of these things, 1/6. Pi equals 1/6 plus or minus A for A being greater than 0, subject to the constraint that each one of these vectors has to sum to 1. All right, I'll let that go to sleep right now. And I'm going to keep this thing right the same. I'm also going to keep this prior the same under J, except I'm going to portion out this 0.01 probability so that all of these other hypotheses sum to, in other words, the sum of the probabilities of E, B, J, given my background information, equals 0.001. Now that's maybe good or maybe that's bad. You may want to weight those hypotheses where the A is very small, not very large departures from symmetry, to give them more weight than ones that are obvious. Because in the end, some of the particular vectors we might get out of this might be, I forgot exactly what it was, but like for instance, we got 0.92 for the 6, and the other ones are all various other numbers. It all adds up to 1, but that's quite a large probability for the 6. We would notice that kind of a thing. And so maybe you want to give that less prior weight than all of the others. But for now, I did not do that, okay? Because that depends on the decision uniform. I left every one of these possible hypotheses equal probability, divided up between this. Now, in the code that I'm going to give you, you can pick whatever you like for these two. And this will automatically divide up whatever you pick the probability for the good, whatever prior that you think they're mostly symmetric. You can use 50-50, you can use only 10%, you can use any number that's between 0 and 1, between 0 and 1. Obviously, if you say it's absolutely false, then it can't become true. If you say it's absolutely true, then it can't become false. So it's got to be between 0 and 1. So you pick it here, and whatever probability is left over is apportioned equally to all of these other things here. Now, I chose two discrete values of A. Now, this is the continuity problem here. If I could do this for every possible A, there's an infinite numbers of A. But that won't be the case in real dice. I cannot deduce probabilities such that the weight is asymmetric in an infinite number of ways. So if I do come up with a limit approach to this, or use continuity in any way, I'll be making an approximation to this discrete and finite reality. Okay, those limits are always approximations to the discrete. The discrete are not approximations to the limit. We started off with that. We got to keep that in mind. So I used a couple of them. How many different hypotheses does this generate? If you pick an A equals 0.02 and generate every possible P that does this, you get like 2 million different hypotheses. If you let A equals 0.01, I don't know if you can even see this anymore, you get like 72 million or 71 million, I guess it is. Maybe it's 72, I don't remember. You get 72 million hypotheses. Doesn't matter though. I mean, it's just math. But in terms of efficiency, numerical calculating efficiency, you can play with this code. You're going to have to just accept my word for it right now. It doesn't really make much difference. I get the same answers for most of the scenarios that I tried. But of course, your scenario may be different. There's no universal answer. I cannot stress this enough. Over and over, and I'm trying to tell you, there's no universal answer. Right? One does not exist. It just does not exist. There is no universal. It depends on the hypothesis you consider, and there's nobody out there telling you which ones to consider. There's no science that directs one way or the other, except for some knowledge about physics that we have. Given all of these possibilities here and giving them all equal weight and so forth, I then calculated the probability the die is good. And also the probability, what's the most likely bad scenario. And for reasons we're not going to talk about today, but I write about, it's always the observed frequency. All right, you know, it's going to be this frequency, 1, 2, 3, 4, 5, 6 divided by 21. Each one divided by 21. That's the hypothesis, because of course that's what we saw. Therefore, that's the most likely. That generates the data that has the highest probability. That generates the data that has the highest probability, not the hypothesis that has the highest probability, you understand? So I want to calculate the probability the die is good, and then all I got to do to calculate the probability the die is bad is take 1 minus this, and I just do this. And this is the real trick down in here. And I have the code that does this, and I ran this code for these particular scenarios. This is much more realistic. And I think it's probably what Willis really wanted. I want the probability the die is loaded. This is the probability the die is loaded for all kinds of ways of loading when we don't know the exact way it's loaded. But we do know that it's loaded somewhat because of J, because of our knowledge of the physics. Okay? So here we allow, and the smaller we allow A to be, of course, the tighter this becomes, but the answer doesn't change very much, okay? Because we're, you know, we can allow 0.0001. The problem kind of explodes, gets big in a hurry, and the answers don't change very much because these are all just, you know, numbers that we're calculating and so forth. So I did this. I think, let's see here. The first one is. Okay, oh, that's a different one. I actually do more in the write-up. You'll have to go and read it. I'm not going to put it on here about how, if I wanted to consider just 2 bad ones at a time, for instance, or 3 or 4. It's just Bayes' theorem all over again. But this is the real meat of the question. So I did this one for a more realistic thing. 21 throws of a dice didn't seem realistic, so I did an M equals 2. C equals 2 for this. In other words, I saw 2, 4, 6, 8, 10, 12 in each of these slots, and that gives a 42, an N of 42. Maybe that seems like a more reasonable experiment size. And using these particular weightings, the probability the dice is bad, this probability, the 1 minus the probability is good, turns out to be 0.000, 3 zeros and a 6. When A equals 0.01, okay? When A equals I kind of misspoke up here. It's not just this. It's not 1/6 plus or minus A. My apologies. Here's how I wrote the code. Equals A. Please forget, I don't want to go back and edit that out. It doesn't make any real difference, except for when you go in the code, you say, hey, where's the plus or minus 1/6? No, it's A. A can be any probability. That's why it doesn't look, why didn't I choose 1 in 1,000? Because I'm letting A be a 0.01 or 0.02 or 0.03 or 0.04 and letting the other ones all things. So I want to calculate all possible ones. This is not some Monte Carlo Markov chain, none of that kind of nonsense. This is an exact combinatoric solution. I generated all possibilities when A is either 0.01 or A is 0.02. And I did it with 0.01. I got 72 million possibilities. That's, in other words, I have 72 million vectors in which the sum goes to 1, and I have all of those other things, all of which would indicate a loaded dice. They're all not symmetric. None of those 72 million are 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, okay? Now with A equals 0.02, which saves a lot of computation time, now I've only got 2 million possibilities to check. I get pretty close to the same thing, 0007. This is actually 0063, and so on. So it's close enough, I would think, for most people. And that's if, here, and you want to stick in others, you want to stick in other observations that you particularly got, well, you stick the data that you got in there and you'll get your calculation. I'm going to go through this one more time because it's complex. I'm going to have the code on the site, and you can go through this. But again, I think we've reached what Willis meant when he asked for a loaded die. And it was always what I told him. I said, you got to pick some level of departure and you calculate the probability that you see that, and then use Bayes' theorem. It's just Bayes' theorem is the answer in the end. Of course, I was very lazy about that, so I'm very happy that he insisted that I provide this answer. And it took a lot of time just to get this particular answer, but I think it'll be fruitful in further discussions that we have. So I love that kind of pressing me. It really helped, I think. I think it really helped us because we're learning to think physically. We're learning to think about the real world versus this fantasy world where probability is a cause and so forth. What does loaded mean? It means the dice has departed from symmetry. We're not worried about the departure from symmetry in the method of tossing, the manner of tossing, I should say, or in the milieu. Although those are real and important, we're going to assume somehow they're handled by some robot or something. We're ignoring them. We're interested in the die itself, or dice itself. Are they loaded? That means a departure from symmetry in those causes that make the face come up one over another. We deduce the probabilities. If it is symmetric, we deduce the probabilities 1/6. Every state is 1/6. The probabilities are not there. We deduce these probabilities from the hypothesis, not the other way around. Loaded means, well, we have a departure from symmetry that we may deduce any of these other probabilities, such as the probability, for instance, one of these probabilities is, if I'm doing 0.01, one of these probabilities is 0, 1, 0, 1, 0, 1, 0, 1, 1, 2, 3, 4, wait, 1, 2, 3, 4, 5, and now we got 1, 2, 3, that's 0.05, and this will be 0.95. That's a particular probability I checked. That's a particular hypothesis. The hypothesis is the die is itself loaded in such a way to give 6 a lot of weight. And every other possibility that we have in increments of 0.01, and then I did it again in 0.02 because it saves quite a lot of computation time. We consider all those hypotheses and we give them whatever prior weight that we want. It doesn't have to be 0.01. I divided that 0.01 up into the either 2 million or the 72 million. In other words, each one got either 0.01 divided by 2 million or divided by 72 million. But if you want to do 50-50, if you think you got shady dice from a candy store or something, well, then you might want to use something like 50-50. And that 50% would be divided up among all these other possibilities. And then we calculate the probability of the data that we see, whatever we're going to do, however many rolls we're going to take, doesn't matter. Conditioned on the die being symmetric. And then we multiply by whatever we thought we were going to see, the prior probability. Again in the denominator. And then we sum over all possible loaded conditions. Then we calculate the probability the dice is good. Based on what we saw, conditioned on what we assumed about the problem and what we saw. And we take 1 minus that, gives us the probability the dice is loaded. And I think I did, what else did I do here? Oh, I did others. If you do multiply this by 10, in other words, you get 10, 20, 30, 40, you see 50, 60, the probability of the dice goes, it's not 0.996 or something like this. The probability the dice is loaded rapidly goes to 1. Okay, so it doesn't matter what prior you have. Even if you have this dinky little prior right here, this probability that the dice is bad rapidly goes to 1. But the answer was always, you calculate the probability of what you wanted to know. The p-value does not tell you that. The p-value tells you, assuming some bizarre equality in parameters or some null hypothesis, it tells you, here, calculate the probability of data we did not see. And then what? How about just calculate the probability of what you want to know? And it led us to think about very carefully what's going on with this dice, or these dice, or this die. It's a physical process. It's a physical process. We're after cause. Part of that cause is the material of the cause. And we led us to think about symmetry and all this kind of a thing. And it led us to think about what did we mean by all these hypotheses and so forth. It was really, this is the entire class. This is the entire class that I'm teaching you, uncertainty, here in now 80 minutes. So much for a half an hour. 80-minute class of uncertainty right here, which get the entire thing. Every other problem we're going to do from now on is exactly like this. It's exactly like this, just in more detail and different problems. In fact, we learned from almost day one, I have the link to it, from the first couple of weeks we learned that had to be the answer to all problems. You calculate the probability of what you want to know, given the evidence you assume. The probability of what you want to know, given the evidence of what you assume. That's what probability is. What you want to know by the evidence you assume, that's what you calculate. And it doesn't mean it's easy. The code for this, in fact, just as an aside, I was having trouble keeping track of all these, so I was using Grok actually to make sure I got the right answers to some things. And it's terrible. It's terrible. I say, could you generate the code for such and such using these constraints and whatnot, and proper form and all this kind of a thing. Oh, great, here's the answer. Lots of exclamation points, completely wrong, completely wrong. And I said, no, this is wrong. Each of these rows have to sum to 1, and the other constraints have to be met. Oh, you're right. Here, well, here's the 100% bulletproof code. And then I look at it again. No, you're wrong. It has to be this. You're missing all these things. You have to meet all the constraints. Oh, you're absolutely right. Oh, yes. Now here's the final 2025 tested. And I went back and forth like 5 or 6 times, just because I was interested to see how this was going to work. And in the end, it gave me code that worked, but only because I knew the right answer. All right? Because I knew what the right answer was going to be. And in fact, it used a different package that I hadn't considered using. R has, I don't even know how many, thousands of packages down there. You can just load and do things that somebody has already thought of these problems, these combinatorial problems. And so I used that one, and I got it's just a little bit cleaner code. For teaching purposes, I think it's more useful. But if you try to use those things and naively just think, okay, I'm going to use this, I gave it the right thing, and it looks right, and it even spit out, the funny thing about this for those people interested in Grok, it said, here, I tested this code, and here's the answer, and the answers looked right. So you think that code, what is he doing? What is the model doing? They got this model saying, here's the code. If you run this code, which the model claims it did, it spits out the answers, which are correct. All right? But when you run the code yourself, the answers are not correct. The answers are way off. So for instance, I was getting one vector, I think it was 0.024. 0.024. 6.024, that doesn't sum to 1. And it kept doing that kind of a thing, but claiming in its output that yes, indeed, it was summing to 1, and it looked like it did. So you have to keep at it. You have to keep at it. And I'm worried now that they're using their clean version of the code that I missed something, so maybe if I did, one of you guys could find it. But I think it's okay. It seems to give all the right answers to the questions I put to it, but that doesn't mean that it really is bulletproof. So those AI engines out there, they're useful in making clean-looking code. They're very useful at that. Boy, it comes out real pretty. It really does. But it doesn't mean it's right code, which is what you really want. Who cares if it's ugly? All right, that's it. I think I've beat you to death. If anybody has made it this far and made it all the way through, well, God bless you. I'm glad that you have, and I hope that you go back and look at the written lecture, which is at wmbriggs.substack.com or wmbriggs.com, and you can study this in depth, and that's where the code will be, the code that I got from Grok. I modified in various ways, and you could use yourself. Now you have code to check. If you just input, is the die loaded, you input this, and you input your priors, and if this scenario fits what you mean by loaded, because it doesn't have a definition, that's part of B. What you mean by loaded is part of B. There is no universal definition of loaded, okay? I have to insist Over and over and over. There's no answer. There's no right answer. It depends on what you're doing with the data, and it depends on what you assume, what evidence you assume. You change any of it, including what you mean by loaded, and the probabilities change. That's not a bug, that's a feature. All right, thank you very much, and thanks for putting up with me. Bye-bye.